Hello and welcome everyone to another session in the DataHour series. We are thrilled to be here with you this evening for a session full of action-packed learning. I am Mahima Chaudhary, part of the data science team at Analytics Vidhya. So I'll be moderating today's session. For those who have joined us for the first time, a brief introduction to the DataHour sessions. The DataHour is a series of webinars conducted by Analytics Vidhya and led by top industry experts. It is a fun way to understand the concepts of data science from the leading players in the data tech domain. And as the name suggests, it's 1 hour dedicated to data. We are hopeful that these sessions are going to be a great source of enrichment and value adding for our community members. Now on to our session today, which is building machine learning models in BigQuery. In this DataHour, the speaker will review how Google Cloud BigQuery supports regression classification, forecasting, dimensionality reduction, and collaborative filtering. Thus, the session concludes with a discussion of good practices for building and serving machine learning models in Google Cloud BigQuery. Before we kick things off, and I hand it over to our speaker, a quick recap of the housekeeping items. We are recording the session and the recording will be available on our YouTube channel, for which I have provided the link in the chat section. Please use the Q&A section for asking any questions you might have during the session, and we will do our best to answer them as the DataHour progresses or towards the end. Lastly, we will share a feedback poll towards the end. You all are requested to kindly fill that up before leaving the session. Now on to our speaker. In this session of DataHour, we have Dan Sullivan with us. So Dan is a cloud and data architect with extensive experience in data architecture, data science, machine learning, stream processing, and cloud architecture. He's currently working as principal data architect with 4 Mile Analytics. He's also the author of official Google Cloud study guides for the professional architect, professional data engineer, and associate cloud engineer. Over to you, Dan. The virtual stage is all yours.
Thank you. If you'd like to turn on and enable my video, I will be happy to share my screen.
Right. I'll just.
And thank you. While we're working on the sharing issues here, just wanted to say thank you for the opportunity to talk with you. I'm very excited to talk about BigQuery and machine learning. And really, one of the things that interests me the most about it is how it opens up the sort of the landscape of machine learning to a much wider audience. So it's basically, if you know how to use SQL and you're familiar with relational database concepts, you're well on your way to being able to work with machine learning and BigQuery. So let's see. All right, we're still working on the screen sharing issue here.
Yes, Dan, I've provided you the remote controls. Please go ahead.
Okay, I am not able to share screen. I'm just getting a message that a host has disabled screen sharing.
Okay, let me check. Can you check it for once?
Okay, yeah, it's still disabled for me.
Okay.
Well,
yes,
I will say, oh, there we go. Okay, maybe this is, we have maybe some change here, share screen. Oh, there we go. Okay, let's share that. And we'll jump to this. Let's see what we have here. There we are. Yeah. Okay, great. So thank you again. I will say this data hour will be more like a data half hour, I'm afraid, because of a last minute conflict that has come up for me. But let's just jump in right now and let's talk about machine learning and BigQuery. And basically, when we talk about machine learning, we're really talking about machine learning engineering. So this is less about getting into the sort of the intricate details of how any particular algorithm works, but it's more about the larger flow of how we actually build machine learning models. And here's an example where we can see the basic steps that are involved. So we have some data that we're working with, and we want to be able to extract features, split our training set into a subset of data that we can use to train on, and then another set that we'll evaluate with. And in BigQuery, the advantages we have, or what bring BigQuery ML or BigQuery machine learning brings to the table, is that we can create machine learning models in SQL. So prior to this, really, I mean, your choices were to work in a programming language like Python or Java or another language, traditional programming language. But with BigQuery, we can now work with SQL. And while we're in BigQuery, we can actually build several kinds of models, including sort of some of the most popular like regression and classification and clustering. But we can also do things like time series forecasting or collaborative filtering for recommendations. The big advantages of using BigQuery ML is that it allows SQL users to build models. So it really democratizes access to machine learning. There's no need to program in Python or Java, as I mentioned. And another big advantage is when you're working with really large tabular data sets, it's really helpful to not have to export the data. BigQuery is a wonderful tool for managing large data sets. So we can use it for a variety of different use cases in business, from forecasting demand for different products, making recommendations for products, detecting anomalies. So let's take a quick look. So what do I mean when I say we want to be able to create a machine learning model in SQL? Well, basically what Google has done is they have extended SQL and added data definition language statements. So they've added a create model statement. And when we create a model, we can specify a name for our model, and we specify a set of options, which includes like what type of model we want to build, and where our labels can be found. And then we specify a data set or a result set from a select query. So here, for example, we're selecting weights of newborns, and we're trying to build a machine learning model for predicting the weights of newborns. Now, once we have a model, let's say we have a large set of data and we are able to build a model, we can then predict, or we can use the model that we've built to make predictions about other data sets. And the way we do that is we use a function that is in the ML library. It's called ML predict. And we pass to the ML predict model the name of the model that we had built, and then also a select statement with the attributes or the features that we use to train the model. So basically, it's the same select statement that we use to train the model, but without including the label column. And that's basically it. That's the core of how we build and use machine learning models in BigQuery. Now, there are other features or other extensions that Google has brought to the table in terms of supporting other aspects of the machine learning pipeline. So for example, the early stages, when we have that raw data and we extract features, well, a lot of times there's a lot of feature processing that we often need to do. And so there are several functions. For example, we can use bucketize, which basically allows us to, say, segment continuous values into discrete ranges. So if we had a feature that had a value from, say, 1 to 100, and we wanted to break that down into 10 buckets, we could create ranges from, say, 0 to 9, and then 10 to 19, and 20 to 29, and so on. And bucketize would handle that for us. We could automatically map from a continuous value into buckets. Now, another useful feature, especially with tabular data, is something called feature cross. And a feature cross basically allows us to combine 2 or more attributes into a new attribute. And this is useful when there are nonlinear relationships in the model, and we want to try and capture some of that nonlinearity. So for example, if we were working with geographic data and we had a longitude and latitude as two separate features, we might miss things, or it might be harder to learn certain concepts that are related to longitude and latitude. But if we combine them into a single feature where we have both latitude and longitude in a single feature, we might get much better performance. And that's the kind of thing we do with feature crosses. There are some other extensions as well. The ML trial info and evaluate and detect anomalies are all other additional functions that support, for example, running multiple trials or evaluating the quality of a model. Or in the case of ML detect anomalies, it's a fairly high level function that allows us to use things like clustering techniques to determine outliers or anomalies. So let's take a quick look at the type of algorithms, that we have to work with. We have both regression and classification. Now, regression models are used when we want to predict a value. So for example, we might want to predict the value or the price that a house will sell at some point in the future. And we'll use features like the number of rooms in the house, the total area of the house, and things like that. So we would use regression like linear regression or some other regression algorithms for that kind of prediction. In classification problems, we have a label or some information or some category about a particular thing. So for example, we might want to classify YouTube videos as either a YouTube video is about cats or it's not about cats. And that's a simple binary classification algorithm. And there are, again, many different algorithms we can use for classification. Now, in general, if we work with unstructured data like images, videos, natural language text, those kinds of problems, unstructured data problems, generally work well with deep neural networks. The other algorithms that we work with, like boosted trees and auto ML tables, they work really well with tabular data. So if you have unstructured data, then probably deep neural networks it will give you good performance. If you are using more structured data, for example, like what we do in BigQuery ML, we can often use boosted trees. For example, XGBoost is particularly adept at building good models in many different cases. Now, BigQuery also supports something known as auto ML tables. And auto ML tables is part of Vertex AI. Now, Vertex AI is part of is basically Google's machine learning platform. And there are many components to Vertex AI. And so one of those components, auto ML tables, is made accessible to us through BigQuery. Now, clustering is another algorithm or set of algorithms that are available to us. And basically with clustering, what we try to do is basically perform unsupervised learning. That is, we don't have labeled data. We simply have a data set and we're trying to discern or understand some particular characteristics of that data. For example, are there subgroups that tend to fall together or tend to naturally group together? There's another type of algorithm. It's known as matrix factorization. And this is used for collaborative filtering or making recommendations. So for example, if you have some customers who you know have bought certain products, you might be able to use that data with collaborative filtering to produce a model which will predict what other customers might be interested in based on their past purchasing patterns and what we know about other customers who have bought certain combinations of things or have certain particular interests. Now, time series forecasting is really important in the sense that there are many applications for it, especially in business. And the BigQuery ML supports an algorithm known as ARIMA Plus. And ARIMA Plus stands for Autoregressive Integrated Moving Average. And that's really a big, there's a lot packed in there, but basically, when we say it's autoregressive, that means that we're using the feature that we're trying to predict. We use that feature as in our forecasting or in our model. So it's basically, that's the auto part. We're using the same feature. And it's integrated, and it's a moving average in the sense that we look back a certain window of time to try and predict the next point in the future. And as we can see here in this diagram, we have a sort of a trending up kind of indication among this in this particular time series. And so one of the things that ARIMA Plus does is that it allows us to kind of take into account trends and seasonality as we're making predictions. So we'll jump into a little bit of ML in practice here. There is a paper that came out several years ago, and it was written by engineers, machine learning engineers at Google Cloud, and basically, or at Google, excuse me. And what they had found is that in their work, building the machine learning code was a relatively small part of the overall amount of work that needs to go into supporting machine learning models in production. And so in many ways, this is similar to what we find in software engineering, where we write code, but we also spend a lot of time testing that code, working with version control systems, deploying through CI/CD pipelines. There's just many different pieces, and basically deploying infrastructure, for example. And there are analogs to those processes in the machine learning world as well. And it's not surprising, both software engineering and machine learning, we're building services or applications. We just use different techniques for it. But at the end of the day, we're deploying software. There are certainly significant differences, but there are enough similarities that we can see, for example, overlaps. Like in machine learning, we also have to think about how we're going to configure our infrastructure and how we're going to monitor and how we're going to be doing testing and debugging. Well, how we do it and how we do those things in machine learning, again, is similar to how we do it in software engineering, but there are significant differences. So I would definitely recommend this paper. I have the link in the URL at the bottom of the screen. But it's basically, it's a paper on tech debt in machine learning. And it was published in 2015, and definitely it's still reading even 7 years later. Now, another thing we need to do when we're building machine learning models is we need to be able to handle data that isn't quite as we might expect it. So for example, we often have to deal with missing data. And what we mean by that is that there could be attributes or features in our data set that are missing. And there are several ways we can deal with that. In the case of time series data, if, for example, we have, say, IoT data, we're getting sensor data from sensors that might be, say, reporting temperature, humidity, and air pressure in certain locations. And we get some data points, and then all of a sudden we stop getting data points, and there's a gap. And then the question is, well, how do we handle that gap when we're trying to make a forecast? Well, one common way of working with missing data in time series data is just to carry forward the last known value. So for example, if we have the temperature at one moment in time, but we don't have it for the next moment in time, we just simply carry that data forward, and we keep carrying that data value forward until we start getting values again. That approach works well with time series. It doesn't work as well when we're, say, have a mix of, different examples from different instances of things we're trying to classify, but there's no real order to it. So other things we can do is we could look at the most common value. So for example, if we are looking for an attribute that is a categorical variable, And that categorical variable has, let's say it has 5 different possible values. Well, one of those values might be by far the most common. Well, in that case, we could simply choose that most common value and use that to impute the missing data. And there are several other techniques, but these are things we need to think about before we even start applying our machine learning algorithm, because we need to understand, what our data is like and what kind of problems might be lurking in that data, for example, with missing data. Other techniques we want to do, we want to use things like standardization and normalization. And we do that when we have values that are in kind of different scales. So for example, if we have something, values that are variables or values that are in the range of say 1 to 10 and other values that are in the range of 1,000 to 10,000. Well, those larger values could easily throw off or outweigh the smaller values. So we tend to want to kind of map everything, all of our continuous numeric values into a range of like 0 to 1 or -1 to 1. So that's another thing we need to do with regards to feature engineering. And then also, oftentimes we want to encode categorical variables. So if we have values like red, green, blue, and we want to say work with a deep learning network, well, we need to map those categorical values into a representation that we can actually use with a deep learning network. And with deep learning networks, all of our data is encoded basically into a vector, a numeric vector. And so we want to be able to encode those categorical variables. And one common way of doing that is called one-hot encoding. And what that means is if we have 3 possible values, red, green, and blue, we assign a value to each of them. So for example, red might be 001, green might be 010, and blue is 100. So we have 3 distinct values, maps easily to a numeric vector, and so we can readily use that with a deep learning network. So those are there are other things we can do with categorical variables as well, or other encoding methods, but that's a popular one, the one-hot encoding. Okay, another thing we need to be aware of with machine learning is something known as hyperparameter tuning. And hyperparameters are parameters that we need to set before we start applying the algorithm and start training a model. Now, in general, what we do when we're doing machine learning is we're learning parameters in the model. So for example, we're learning weights assigned to nodes in a deep learning network, or we are learning optimal configurations of trees and depths of trees in say a random forest. But then there are other parameters that aren't learned. They have to be known at the beginning when we're starting to apply our algorithm. So those are hyperparameters. And so with hyperparameters, some of the things we can set are when we're using linear regression, we can use techniques called regularization to help avoid overfitting or having the model really almost memorize the training data and not generalize very well. So regularization helps with that. And there are two commonly used regularization algorithms are L1 and L2, and we can choose which of those we'd like to use. We can also, when we're working with clustering, we get to choose the number of clusters. And then also when we're working with deep learning networks, we can set things like the learning rate, which is like when we detect an error and we're adjusting our weights, how much do we adjust? Do we make small increments or fairly large increments? That's determined by the learning rate. Now, regularization is also used in deep learning. Another technique that is used in addition to regularizations like L1 and L2 is we could use something called dropout. And that's a kind of way of avoiding overfitting by essentially turning off some nodes in the network as if they were dropped out or no longer in the network. And that is a technique that has turned out to work well for helping to prevent overfitting in deep learning networks. Now, something that we're all sort of becoming much more aware of, I think, in the machine learning community is the need for being able to explain why our models make the decisions that they make. This is especially important if we are making decisions that, say, can affect whether someone in a significant way. For example, will someone be hired or not hired into a particular job? Will someone be offered a financial service or not? And when we make algorithmic decision or use algorithmic decision making, we need to be able to explain why we do that. So explainability is a key aspect of machine learning that we need to think about. And there are different types of explainability. We need to be able to explain like what data we used and why did we use that? And was that data actually representative of the population that we're trying to understand? There's also, we want to be able to explain our predictions. So if there is a prediction that says, no, I wouldn't be suitable for a particular job, we need to be able to explain, what features, what are the things that the algorithm considered or the machine learning model considered when deciding, no, I'm not suitable for that job. Was it my lack of years of experience? Was it particular domain knowledge that I didn't have? We need to be able to, the algorithms need to be able to provide us with information about that. So so explainability is just something we also need to keep in mind with regards to when we're working with ML. So some problems to watch out for, underfitting and overfitting. I briefly mentioned overfitting, and that's when a model basically learns the training data set so well that it fits the training data very well, but it doesn't generalize. So when we use that model with data we haven't seen before, it doesn't do nearly as well. So that's overfitting. Underfitting is when our model is not able to learn sufficiently to actually distinguish, say, make correct classifications or make a regression prediction accurately. And the way we address underfitting is we make our model more complex. We basically do things like add more layers or nodes to a deep learning network, or we expand the number of trees in a machine learning, say, a random forest, or we increase the depth of the trees. Other problems to watch out for are in time series forecasting. A real tricky thing is what's known as exogenous variables. So, for example, we might be looking at the sales of a particular product over time, and we might see a general increase. And there might be spikes. There might be times where there's a significant increase in sales, and we might not know by just looking at the data on the number of sales, what is the reason for that sudden spike? Well, that sudden spike may have occurred because someone had a marketing or a sales campaign and offered a sale on a particular product or other incentives for people to buy it. Well, the fact that someone sort of essentially altered the state of the world and created new incentives for people to purchase a product, that's outside the data that we have. So that's an exogenous variable. So those can be really tricky to work with. So we have to be careful watching for those, especially in time series forecasting. And then finally, we need to watch for bias. So we want to make sure, if we do have a data set that we're working with, and it's say for predicting who we want to hire in particular jobs, we want to make sure that our sample, the data that we're using, our training data, is actually representative of the population that we're working with. So that's just one example of bias. There are other kinds of bias. We might exclude data. So for example, we might have some missing data and in some attributes, and we might decide, well, we're just going to ignore those rows or those instances. But there may be reasons that data is missing. For example, there might be some characteristics. There may be, say, for example, a driver's license number or a government ID number that might be missing. If we were to throw out all of those instances, then we would be biasing our data sample away from people who don't have driver's licenses or for whatever reason don't have that particular government ID. So that's a kind of an exclusion bias. So we have to watch out for that. Okay, before we jump into Q&A, I just want to jump over to show you a little bit of BigQuery in action, a little bit of like what this looks like in BigQuery. So, and I'm sorry, I didn't explain when I first started about BigQuery. I just sort of assumption people are familiar with BigQuery. BigQuery is a analytical database provided in Google Cloud, and it's a managed service, so we don't have to manage any servers. And it was originally designed for large-scale data warehousing. It really scales well up, up to petabyte scale kind of data warehouses. So it works with quite large volumes of data. And so it's ideal for working with machine learning because we can use the data that we have in BigQuery to basically populate or to sort of use it to train as well as to evaluate and then apply predictions. So what I've done here is I've opened up a BigQuery, a project area that I'm working in. And in Google Cloud, the way things are organized, it's basically around projects. And so within this project, I have a number of different data sets that I am working with. And one of them I'm calling BQML training for BigQuery machine learning training. And what we can see here is that I have some data sets. So for example, here is a healthcare analytics training data set. We'll take a look at this. And what we can see here is that we have some attributes about people who have had hospital stays. And what we see here is we have information about hospitals, for example, a hospital type code, a city code for the hospital, a geographic region, as well as some information like the number of rooms that are available, what type of ward or department within a hospital the patient was in, type of information, severity of illness. And what we're trying to predict is, what we could use this data set for is predicting the stay. So if we look a little bit at the data, we can see we have both numeric data, and then we also have categorical values like the hospital type code and hospital region code and department. And what we notice, so these are different features of a person's stay in a hospital. And what we're looking for, or we want to find out or estimate, is what was the length of stay of each of these individuals? And so, for example, the stays are bucketized in ranges from like 1 to 10, 11 to 20, and so on. So the way we would build a model is we would use a, it's use one of those create model statements that we just saw. Let's see if I'm wrong. That is what I want. Sorry, I'm just going to refresh here. I seem to have lost my data sets in the browser here. Training, there we go. And so we were looking at healthcare analytics, this data set, and we were looking at the different attributes. And then what we are also able to do is build models. So basically, when we execute that create statement, kind of like I had used before, we build a model. So the model itself is an abstraction or an entity that is tracked in the database. And we can take a look at, these models are for a different one. This is for employee attrition, but we'll take a look at this in any case. And when we build a model, what we can see here is we have this, basically this is metadata about a particular model. And so, for example, here we use boosted tree classifier. So a boosted tree are things like XGBoost. And we can see that we had various training options, like the number of iterations that we want to use, and how we are trying to measure the quality of this. So for example, we're looking at receiver operator curve and area under the curve, which is a common way of measuring classification algorithms. And then we have other information on the hyperparameters. So we talked about us being able to set different hyperparameters. And so here are some examples of that. We can also get information on the training. So for example, we had 10 trials here, and we can see how the loss was in each of the different trials and different combinations of different hyperparameter combinations. And we can see the results evaluations. So for example, when we try a certain set of parameters, it looks like trial ID number 7 was the optimal one. In that case, we had a particular learning rate, and we were able to get fairly high precision of about 0.93. So so these are some of the kind of the information we can get from the results of the model and the model that is saved. And then here again is just this is actually the set of data that was used to build that training model. And let me show just one other. I'll show you a simpler one, which has evaluation. So when we just do one instance, the results that I showed you there was from a series of trials, and we were trying to find optimal hyperparameters. Here's an example where we use some data that is about irises, and we trying to identify the particular species of a kind of flower. And so here we built a simple logistics regression model. And what we find is we had very good precision and recall, about 0.97. And we have information here like a confusion matrix that we can get. This tells us how well we predicted, like what our true positives were. And what we can see here is that we have 3 different labels that we're trying to predict, and we predicted really well for all of them. And that's because the iris data set is very simple. It's sort of like a hello world kind of problem in machine learning. So this is the kind of information that we get after we build the model. So in terms of working with the evaluation, the kind of things we want to do with that, this is the kind of information we can get. Now, I'm going to, if we have questions, I see there are some questions. We have a couple more minutes. I will try and answer these. And please feel free to message me on LinkedIn. My ID is Dan Sullivan PDX. Let's see. Here are some questions. Is it correct to replace an outlier with a mean value? It depends. That's a good question. And it depends. That could be if for some reason you think that outlier is a measurement error. So you believe, for example, that something is wrong with the sensor. It's telling you have a reading of 90 degrees Celsius when it really shouldn't be any higher than maybe 40 degrees Celsius. So you might decide that really is most likely a measurement error. So in that case, using the mean of, say, the most recent values would be a reasonable approach. In other cases, we have to be careful because that outlier might be actually correct and it's telling us something. So for example, it might be a very high temperature, but in this case, the high temperature indicates that some other part of the machine is failing and it's not cooling properly. So in that case, we don't want to replace the mean value. Let's see, what imputation method did you say is best for time series data? That depends. You could, carrying last value forward is the simplest. Another common one is to use moving average. So say, look at a window of, say, maybe the last 3, last 5, last 10 values and average those. That's another common method. Oh yeah, great point. Is it always advisable to apply imputation techniques to real-world data sets? Doing so will introduce some form of bias. You're right, it will. And so it's a matter of trade-offs. So for example, if we say we have people that are missing attributes and we don't want to throw the data away, you know, for example, because we, you know, there might be a subset of the population that for whatever reason, we don't have that value for them. So either we don't use the value, that feature in our training set, or we need to come up with some way of sort of informing, making a best guess. So yes, we are risking introducing bias, but it's almost like it's a balancing act because we're trying to avoid even worse bias. So yeah, I think that's an excellent question, and there is no simple answer to that. Can you show how to add hyperparameter tuning into a script? I'm afraid I have to go to a meeting in 1 minute, so I won't be able to do that one. How do we add cross-validation to the SQL script? I would think if you, in both cases, it's documented. If you look at the BigQuery ML documentation for create model, you will see examples of how to do that. And all the parameters, like how to use different parameters and stuff, is documented there. So I'm sorry I have to run, and I'm sorry that was such a quick overview. But again, please feel free to connect with me on Dan Sullivan PDX, and I'd be happy to answer any questions. And so I'll stop sharing and turn this back over, and thank you again for hosting.
Thanks a lot, Dan. I would like to share a feedback poll. So I would request all the attendees to please answer the feedback so that it will be helpful to us for the future data sessions. And thanks a lot, Dan. On behalf of Analytics Vidhya, I would like to thank you for your time and for delivering such a wonderful session. I'm sure our audience found it insightful, and hopefully we can conduct more such sessions with you in the future.
Thank you. Take care, everyone. It's great to see you. Take care. Bye.
Thank you. People, please fill in the feedback polls and let us know how was the session. Thank you everybody for joining in. We'll be back with another session of the Data Hour on 21st September, that is tomorrow. The link is in the chat section. Till then, bye-bye and keep learning. Take care.